The strange sounds you hear in the background, we hesitate to call them music, and you certainly wouldn't want to dance to them, represent mathematics, whose acoustic renderings are what this paper by me, Michael Berry and Pragya Shukla is about. The paper is called Hearing Random Matrices and Random Waves. The context is the observation that visual and auditory perception are different. If you compare mathematics and physics paper from a century ago with those of today, one difference you immediately notice is that the modern papers contain many more pictures. There are two reasons for this. First is the growing recognition that while an equation is a compact summary of a complex idea, its very compactness can make it hard to appreciate. And a picture, traditionally worth 1,000 words, can help us grasp its content. The second reason is that with modern software, it's quick and easy to make pictures rich in information content. By contrast, although there have been a few representations of mathematics as sounds, our sense of hearing has not been systematically investigated as an aid to the comprehension of mathematical concepts. Our renderings represent two areas of mathematical physics. The first area is random matrix theory. This is a way of characterizing energy levels in quantum systems, quantum chaology. That's the study of quantum systems whose classical counterparts possess chaotic orbits. More generally, it characterizes eigenvalues, that's a mathematical property of vibrations, of systems whose vibrations are complicated. Random matrix theory represents the energy levels in a way that captures their statistics. There are three main types of random matrix statistics with different fluctuation properties related to the symmetry of the underlying dynamics, and the purpose of this study was to find out if the differences can be heard. To do this, it's necessary to render the energy level sequences as sounds. And there are many ways to do this. One, that we explore in the paper, is to create functions of time whose zeros are the energy levels. Now, even for this, there are many possibilities. We find that rendering the functions as phase modulations of a carrier wave is convenient. There are sets of sound clips, several sets, each lasting a few seconds. Each set consists of 5 clips, the 3 random matrix functions, sandwiched between a function representing perfectly ordered energy levels and one that represents the opposite, namely completely uncorrelated random energies, Poisson distributed. The other way we represent sound is to create sequences of notes from the musical gamut, whose pitches correspond to the spacing between adjacent energy levels. Again, differences between the types of random matrix can be distinguished by listening. The second area that we rendered are random waves in 2 and 3 dimensions. These are made by adding many monochromatic waves travelling in different directions, representing, for example, laser speckle, the blackbody radiation that bathes the universe, quantum electron waves in a chaotic quantum dot. Many examples of random waves. One-dimensional sections of such waves are functions of a single position variable, and if this is regarded as time, the sections can be rendered as sounds, and here again as phase-modulated carrier waves. The point was to learn if waves in 2 and 3 dimensions can be distinguished when represented in this way. We are not experts in sound processing, and we regard this paper as little more than a beginning. Further developments come quickly to mind. More sophisticated renderings, for example, employing rhythm, harmony and timbre, as well as pitch. As we declare in the introduction, this paper is frankly speculative. Whether mathematics is useful or merely a curiosity remains to be seen, or rather heard.